Hello, my name is Marluca Green, and this is a pre-recorded talk for the 2021 meeting of the Society for Mathematical Psychology. During this talk, I'm going to show you the preliminary results from a study on quantifying sources of within-subject variability across different tasks from multiple publicly available data sets. So far, we have almost 1,500 participants with 16 different data sets, and for each participant, we examined how much of their trial variance could be explained by conditional factors and by temporal trends. I'll be showing you the exact methods and results in a bit, but first I would like to talk about the concept and origins of within subject variability. So in a typical experimental setup, researchers are interested in differences between conditions that are directly manipulated by the researcher themselves. So for example, let's say that we have a congruent or easy condition, a neutral one, and an incongruent or difficult condition. And we aim to find that the congruent condition is the easiest. However, when we look at one participant's data over time, we can see that their reaction time is highly variable and that any conditional differences are impossible to spot. And therefore, we call this data set noisy. And to solve this, we extract the mean for each participant to get a true estimate of their performance. And then we repeat this for a larger group of participants. And the result of this process is a clear pattern confirming that indeed participants are faster in the congruent than in the incongruent condition. So from this perspective, within subject variability is seen as noise that should be ignored. However, variability is very interesting on its own. First of all, in real life, we are also variable. And also variability is a reliable individual trait with clinical implications. And most importantly, for the aim of this study, variability does not behave like noise, as we can see from its temporal structures. And to look at this, let's take a time series in which each observation is just random error. And by definition, this time series will not show any dependency over time. This is reflected in the absence of autocorrelations. So for example, the autocorrelation between observation n and n plus 1, so the autocorrelation at lag 1, this will be 0. Now, typically, behavioral reaction time series behave very differently. Reaction time on trial n is partly dependent on reaction time from trial n minus 1, as is shown as the positive autocorrelations at lag 1. And this means that the reaction time series are not noise, but they are temporally structured. Now, part of this temporal dependency may arise from our own conditional manipulations. So for example, here we have a visual motion discrimination task with an auditory cue that could be congruent or incongruent to the visual information. Participants had the fastest reaction times on congruent trials when the previous trial was congruent as well. And this is called the sequential congruency effect, and it has been found across different types of tasks. Now, because these dependencies are caused by the structure of the experiment, we can say that they are caused by exogenous sources. Exogenous here means that the participant's behavior is caused by the environment. Of course, when we conduct the study in the lab, we hope that our own conditional manipulations are the only exogenous source of variability that we have in the performance. So all other environmental factors are kept as equal as possible, and then we aim to maximize the effect of our own exogenous source of variability to get high statistical power. But variability and its temporal structures are also apparent when a participant is performing tasks without condition. So let's say a simple reaction time task. And because nothing happens in this experiment, that is, every trial is exactly the same throughout the entire experiment, the variability and its temporal structures must somehow arise from our own internal system, which is what we call endogenous. Overall, it remains unclear how these endogenously induced trial-to-trial dependencies relate to the immediate contributions of the conditional manipulations. And with the current study, we therefore aim to quantify the sources of within-subject variance in reaction time across a large range of neurocognitive tasks from publicly available data sets. And specifically, we examined the relative contributions of experimental manipulations and of temporal effects. And secondly, we were interested in examining individual differences in explained variance. Now, to quantify the sources of explained variance, we conducted general linear models on the reaction time for every individual separately. And I will now show you an example for one participant, and this participant performed this multisensory motion discrimination task, 1,200 trials in total. Here you can see a few trials of this data set. And for every trial, we have the reaction time, and this is going to be our dependent variable. And for the independent variables, we have 3 different flavors. So first, we have the conditional manipulations. And in this case, these are the coherence level of the visual dots, the congruency of the auditory cue, and the interaction between those two. And then we also have the coherence, congruency, and interaction from the previous trial. So that is the first component. Then we have the autocorrelation. So we take the autocorrelation at lag 1 and at lag 2. So for example, to predict the reaction time on trial 4, we have the reaction time from trial 3 and from trial 2 as independent regressors. And then firstly, we also look at the longer term temporal dependencies using both the linear and the quadratic term. So here we take the trial number as regressor, and this is done in a blockwise manner. So you have 1 to 240 for block 1, then 1 to 240 for block 2, and so on, ending at 240 for block 5 at the last trial. So now we have all our predictors, and we conduct a general linear model. And again, this is done on the subject level. So for this model, we extract the total amount of explained variance. So that is the R squared. And then we run this for every subject. So we get a distribution of R squared values, with our example participant here being represented by a star. So this is the total amount of explained variance by all these three components together. So conditions, autocorrelations, and blockwise trends. And then we also calculate the unique amount of explained variance for each component separately. So for example, to get the unique amount of explained variance for the conditional component, so that is the purple circle, we fit a general linear model for the autocorrelative and blockwise trends only, and then extract that R squared value from the total R squared. And that way we end up with the amount of variance that can be explained by the condition factors on their own. So far, we have 16 tasks, and most of these are cognitive control, some perceptual tasks that we got from places like OSF, as well as our own previously collected data. And these were selected using the following criteria. So of course, we need the raw data at the participant level. And to keep the model somewhat feasible, we only use tasks that have 1 or 2 conditions at most. These conditions have to be randomly or pseudo-randomly presented, so rather than in a blockwise manner. And then we also had some criteria for the number of trials and the number of participants to get sufficient statistical power. So looking at the results, here is the distribution of the total amount of explained variance by the three components together: so correlation, autocorrelations, conditions, and blockwise trends. So these are all the participants from all 16 data sets, and that is 1,473 participants in total so far. Every dot is 1 participant, and the white dot is the median value. On average, we can explain about 13% of the total within subject variance in reaction time with these three components together. And then we also have the explained variance for each component separately and for their combinations. So here on the left are the R squared values from the fitted general linear models. And here on the right, you can see the unique amount of explained variance. So these last three distributions relate to these unique parts in the Venn diagram. Now, to examine if there are any systematic differences between these distributions, we computed Bayesian pair t-tests, and you can see these distributions were very skewed, so the values were logged first. And here are the means of the log values with the within subject standard error from the fitted condition and the fitted autocorrelation. So that's the second and the third distribution here. And then we actually found Bayesian evidence against the difference between the distributions. So the null hypothesis was favored over the alternative hypothesis. And this means that the fitted models from the conditions from the conditions and from the autocorrelations explain the same amount of variance on average. However, when we look at the unique amount of explained variance in reaction time, the conditional component was higher. So on average, the conditional components explained about 1.7% more unique variance than the autocorrelative component. If we look at the other comparison, the blockwise trend component always explained the most variance, with the average unique amount of explained variance of this component being about 5%. So to summarize what you see here, the autocorrelations explain the least amount of unique within subject variance, The blockwise trends explain the most, and the conditions are in the middle. Now, as you can see from the distributions, the differences in explained variance between participants is very large, and everyone wanted to test if these differences could be explained. And for this, we calculated 3 measures of performance for every participant. So we have mean reaction time on the correct trial, standard deviation of reaction time on the correct trials, and total percentage correct. And then we calculate the between subject correlations between these performance measures and explained variance. And this was done separately for each task because every task, of course, has its own scale for the performance measure. So it doesn't make a lot of sense to mix these. So here is an example for one task with the mean reaction times or the performance measure on the x-axis and the explained variance on the y-axis. And every dot is one participant. And then across participants, we calculated the Kendall's tau correlation coefficient. And then we can do this for the other 2 performance measures as well. And this gives us another 2 tau values. And then instead of looking at the total explained variance by the 3 components, we can also look at the unique amount of explained variance for each component separately across each performance measure. So in total, for one task, this gives us 12 correlation coefficients, each one representing the between subject correlation between performance and explained variance. So this is one task. And if we do that for all 16 tasks we have so far, we get distributions of correlation coefficients. So again, here is, as an example, the mean reaction time, the total explained variance for one task on the left. And then on the right, you can see the distribution of coefficients across all 16 tasks. So our tau value of about minus 0.25, therefore this one task would be somewhere here in this distribution of correlation coefficients. And then we compare these distributions to 0 using Bayesian one-sample t-test. If these distributions are not different from 0, that means that there is no overall relationship between performance and explained variance. So here we have the 12 distributions across the 3 performance levels and the 4 explained variance values, with the base factors from the one-sample t-test next to it, either in black to support higher support, reflect higher support for the alternative, or in orange to reflect higher support for the no. What I think is most remarkable so far is that there is a strong evidence for these 2 distributions being lower than 0. The interpretation here is a bit tricky because this is actually the mean of the inverse reaction time. And this means that overall participants with faster reaction times had less unique explained variance by the conditional components compared to participants with slower reaction times. And secondly, participants with less variable reaction times had on average more unique explained variance by the autocorrelations compared to people with more variable reaction times. So to conclude, on average, the autocorrelative components explain the least amount of within subject variance, while the linear and quadratic blockwise trends components explain the most variance, and the conditions were in the middle of that. Together, they explain about 13% of the total variance on average. So for every participant looking at their full trial-to-trial within subject variance, we can explain 30% of that on average with the conditional and the temporal factors, meaning that most of the within subject variance remains unexplained. The differences in explained variance were large across participants, and some of these differences could be explained by performance measures. And as a next step, we would like to add more data sets, particularly we would like to have perceptual and motor tasks, so we can see if there's also a potential effect of task characteristics on explained variance. So many thanks to my collaborators, and of course, thank you for your attention.